Thank you, Ronnie. And our third and last speaker of this first session is Simon Gayther, who began his career at Cambridge University in the United Kingdom, moved to London in 2001, and is currently a professor of preventative medicine at the University of Southern California. He's led many large, integrative, collaborative projects in several consortia, and now is playing a leading role in the development of the Genetic Associations of Mechanisms in Oncology, or the Game On Consortium, and he'll discuss genetics and polymorphisms and other germline events, I imagine. Thank you.
Indeed. Well imagined. Thank you very much for allowing me to participate in this session. And I think I want to start with this very common, well-known family history model of BRCA1 and BRCA2, because we know these are high-risk genes. We know they cause both ovarian and breast cancer. But what I want to point out here are women who don't have ovarian cancer particularly, and how this particular identification of these genetic markers has been so successful in prevention of ovarian cancer. It has saved thousands and thousands of lives. And these were identified in the mid-90s. It's something that many of us have been working on for many years. But of course, the key question is, what other genetic markers are out there that could be used in a similar sort of way for risk prediction and prevention of ovarian cancer? And what we know about BRCA1 and BRCA2 is when you look at the spectrum, the estimated spectrum of heritable risk for ovarian cancer, that they contribute maybe less than a third of the heritable risk of ovarian cancer. And so we're interested, and what I'm going to talk to you today about is this unexplained heritability and how we're moving forward to try to identify the additional risk markers for this disease. Now, when we look at the spectrum of risk, not just for ovarian cancer, but for other cancers, other diseases, you can often draw it out like this, where you've clearly got the high-risk fraction here, but they're very rare alleles. When you look at the increasing allele frequency here, BRCA1 and BRCA2 are pretty rare in the population, but they're critical because they do confer particularly high risks, and so that's why they've been so valuable in families with disease, but they do mainly cause familial ovarian cancer. So what about other levels of risk? Well, we are now coming into a situation where we can start to identify intermediate risk alleles in the population, largely through large collaborations like the Ovarian Cancer Association Consortium, where very large sample sizes are required, but also because of the advance of genomic technologies. And so this is enabling us to now identify moderate risk variants. These appear to be normally coding, just like BRCA1 and BRCA2. We are doing lots of studies, and I'll get on to panel testing in a minute, where we are finding mutations in candidate genes, which we know to be associated with BRCA1 and BRCA2, homologous recombination, Fanconi anemia. And we're also in an era where we can perform whole exome and whole genome sequencing for further discovery of additional candidate susceptibility genes for ovarian cancer. And I want to present you some data, which is unpublished, as well as other published data, to talk about what value that might have. But first I want to step into the rather controversial era of panel testing, which has become very much commercially available. It's being delivered to clinics as a way to identify truncating functional mutations, they're called, in patients who may be at risk of disease, not just for ovarian cancer, but also other cancers. And these are two commercial tests that you can go out today and buy, and you can test your patient for all of these genes. But what does this actually mean? These are cherry-picked genes because we think they're important in disease, but there are many questions for all of these genes which need to be answered before we can actually use these to define a patient who's at risk. Of course, what we don't know for many of these mutations when they're found is, are germline mutations more prevalent in cases compared to unaffected population controls? And what you'll find for lots of these panels, all of these panels in fact, is that's largely an unanswered question. These studies have not been done in large case control series. Do mutations show proof of pathogenicity? Well, I think whole genome and whole exome sequencing studies are now showing that we are riddled with genetic variants. Some of those are coding, some of those are truncating. Many of those actually don't seem to have any involvement with disease. So a truncating mutation does not necessarily mean a functional mutation. And finally, are the disease risk estimates substantial enough to warrant clinical intervention? And this is the key point. Just finding a mutation isn't important. knowing that it's functionally significant is very important, but also knowing that that mutation confers a substantial risk that, particularly for ovarian cancer, you can advise a woman that it's time that she had her ovaries removed. So these are some results from large population-based case control ovarian cancer case control sequencing studies. And what I'm doing here is I'm comparing the frequencies of mutations we found in these studies for BRCA1 and BRCA2 with other candidate genes that we have started to evaluate from some of those genetic testing panels. We picked these genes because we know that they're involved with BRCA1 and BRCA2 from a functional perspective. And what you'll see here is I've represented both the frequency of mutation in cases in red and controls in blue, but also the odds ratios. So what I'm doing here is giving you some sort of idea of the levels of risks which are associated by looking at the frequencies in cases and controls, and then using that as some sort of a parameter for deciding whether you think this is a gene which is important or mutations in this gene are important in ovarian cancer. You'll see that BRCA1 is by far the most significant risk allele, the most significant risk gene for ovarian cancer. Odds ratio of 60, a woman gets prophylactic oophorectomy. BRCA2 also very, very significant in its case control ratio there, but then start to look at some of these other genes. BRIP1 has an OR of 11. It seems to be more common in cases and controls, but certainly nowhere near as common as BRCA1 and BRCA2. RAD51, RAD51C and D, two genes being associated with ovarian cancer. Again, relatively large odds ratios. And they're the sorts of levels of risk which one would associate with potentially clinical intervention through surgery. But we've known about MMR genes for quite a long time and their involvement in Lynch syndrome and ovarian cancer through that syndrome. But in fact, the risks associated with the MMR genes are not particularly high when you start to look from a population point of view. And then you start to look at other genes, and I can tell you that these genes, some of the genetic mutations in those genes are already being used to tell patients that perhaps they should be considering prophylactic oophorectomy. But when you look at some of these genes on a population level, they certainly don't look as significant as that would suggest. Another main feature about ovarian cancer, of course, is we still talk in clinical terms often about this being a single disease. But when you start to break down disease by subtype, you see that the frequency of these mutations, because we know these are involved with BRCA1, BRCA2, and homologous DNA repair, most associated with high-grade serous disease, that carrier frequency is much greater. So going forward in the future, what we're really going to have to do is start doing these studies by subdividing by subtype, because it makes a big difference when you start to do that for non-serous disease. So what about common low-risk susceptibility alleles? Many of you would have heard of genome-wide association studies and the potential impacts that genome-wide associations could make clinically. And what we're looking here now are the low-risk alleles, which are actually very common in the population by comparison to BRCA1 and BRCA2, and so could contribute to a much larger burden of disease. So they're very important to find. These are single nucleotide polymorphisms, but they have an unknown function. They're just genetic variants. The vast majority of these SNPs are located in the non-coding DNA regions, which is contributing to the fact that we don't know their function. And we know that these SNPs are affecting novel susceptibility genes through regulatory mechanisms. So this is starting to highlight the importance of the non-coding genome in ovarian cancer etiology, as it is doing for many other diseases as well. So genome-wide associations have been very successful because people have started to collaborate much better than they used to do in the 90s. And we have the Ovarian Cancer Association Consortium, which has gathered together maybe 50 studies from around the world, has managed to accumulate quite impressive numbers, 18,000 ovarian cancer cases, 30,000 unaffected controls. And of course, when you start to compare the genotypes in cases versus controls using SNP arrays, which are very much available in high throughput these days, you start to find risk-associated alleles with a statistical threshold that tells us that this is causing ovarian cancer to some degree. And so far, we've identified 26 ovarian cancer loci that seem to be associated, particularly with ovarian cancer risk. So this is just a handful of those loci, and I want to point out two features of this table. The first is that the per allele risks associated with each of these SNPs is small. And people will say, well, what use is that clinically? But actually, that's really the mistake that people might make, because although these are small, obviously we have the propensity to inherit multiple alleles. And so if you cumulatively look at those risks, they add up to something that can be quite substantial. The other thing I will say is that while we've identified 26 of these alleles, estimates in breast cancer, for example, suggest that there may be thousands of these alleles out there in the population. So identifying those could be have a major clinical impact in the future on predicting ovarian cancer risk. The other very important feature of these SNPs is that we've started to use these in the laboratory to see what genes are being driven by the downregulation or the overexpression of some of these SNPs in cell line models. And what they are showing is a series of very interesting candidate molecular markers. And this relates quite uniquely, I think, to a novel set of targets which we've not studied before in ovarian cancer. What you'll see is genes like the HOX family of genes, which are associated with development, TERT, HNF1B. These are all genes that seem to be associated with the very early cell, maybe even the stem cell niche of ovarian cancer development, which nicely, I think, brings it back to the first presentation today. A lot of work will be required, however, to see how important these will be in disease etiology. So where are we at right now when I start to roll out this unexplained heritability pie chart again? Well, you'll see that, again, BRCA1 and BRCA2 contribution there is much greater than any of these other alleles put together, but we're starting to see great value in identifying these. And I think we're at the very beginning of these studies, nowhere near the end. There's an awful lot to discover here. We also need to consider how these may interact with environmental lifestyle risk factors. We know, for example, that family history, oral contraceptive pill use, and parity have strong associations with ovarian cancer. We also know other risk factors such as endometriosis, which is associated more with clear cell ovarian cancer, and tubal ligation are risk factors for ovarian cancer. And so we need not just to think of risk as something to do with just genetics, but also to do with other lifestyle risk factors. And can we work that in to models of risk prediction and prevention? And my last major slide here is to see how this model might work. This is work that's been done by Antonis Antoniou and Paul Ferro at Cambridge University, where we are looking at one of those new genes, BRIP1, that seems to be associated with ovarian cancer. When you look at the cumulative risks over an individual's lifetime by age, you see that those risks are actually reasonably good. That may be a risk where you would start to advise someone that they should have their ovaries removed. But when you start to add in the polygenic risk based on the SNPs that we've also identified, you can see the added value of using those SNPs in terms of risk prediction value. And then when you start to incorporate some of these lifestyle risk factors, again, you see that jump in some of those risks, the cumulative risks over a lifetime of someone who has a combination of both those lifestyle risk factors and the polygenic risk factors. So what we're going towards here, I think, in the future is a model where we use a combination of high, moderate, and low risk alleles together with environmental lifestyle risk factors to predict women who have a risk of ovarian cancer that has some opportunity for clinical intervention. The future challenges and the clinical potential of these are multiple, but I just want to highlight a few issues here. We know that there are additional common low penetrance susceptibility alleles which need to be identified. They will require much bigger case control genotyping studies in the future and a combination of some very good statistical geneticists to find the very, very minor associations which may, from a cumulative point of view, add significantly to a risk. And then we obviously need to develop functional work, and I think that the work that Ronnie Drapkin and others have been developing models that we can use really effectively, and we already are using, to actually find novel molecular targets which come from these risk alleles. In terms of the rare, moderate risk alleles, well, we know that we can, although it's still expensive, perform whole genome, whole exome sequencing, and we know that we can do very large targeted sequencing studies. But these studies are going to require, again, very, very large numbers. We've started to work on numbers 3,000, 4,000, but some of those risk alleles, when you look at really trying to identify the true case control differences, may need numbers in the region of 40,000 cases, 40,000 controls to see whether a gene really is important in the etiology of the disease. However, we are at a stage, and I think this is really important, where we could rapidly translate this information into the clinic if we get very good risk estimates and very good population risk estimates, prevalence estimates for these variants and for these mutations. And that has to feed from the research, I think, rather than a company developing a clinical testing panel based on just cherry-picking candidate genes. That's my own personal opinion, but I think it's certainly a very, very valid one when you see the dangers of giving someone information where the research hasn't actually defined what the risk really is. And then, of course, we know the story of PARP. In addition to understanding the etiology of ovarian cancer by identifying novel susceptibility genes and molecular markers, we're also in a position, I think, to perhaps use some of these new molecular markers to develop novel targeted treatments. And then going forward in the future, if we can do this from a subtype-specific basis, then it could be that we're starting to deal with a whole series of molecular markers that can be used for the different subtypes in a treatment basis. So with that, I'll take questions as part of the panel discussion. Thank you.